Welcome to the third lecture on infinite series. We will continue with comparison test, which we started yesterday and proved one part. There is a second part. I will do that, and then we will look at some more basic results which are required about convergent infinite series. Yeah. So this is my YouTube channel. The most important thing you should remember is C for channel followed by Kumar HCU. And you can download the list of all videos in my channel from this thing 4d space mtts.org.in/ea. So it will have the list of all videos, and for each topic it will be given in order, something like first lecture, second lecture, third lecture, etc., so that you will know where to locate, and the URL also given, so it will be easier for you, and it will be periodically updated. And if you subscribe to my channel, whenever I upload the update to this place, you will get to know. Right. So this is going to be the lecture on infinite series, the third lecture, and the reference are as earlier. So let us get started. Yeah. So what did we do yesterday? We did what is known as comparison test. I think I call it comparison theorem. So suppose an, bn's are non-negative, 0 less than equal to n less than equal to bn. This is for all natural number. Now this is the sequence. I have an, bn, then I have associated infinite series summation an and summation bn. Then what do I want to say? What we concluded was, if summation bn is convergent, then so is summation an, the infinite series an converges, and we can assert something more. Let us look at this sum. Suppose this sum is yes, and the sum of this is t, then we are saying s is less than equal to t. Sum of the infinite series an is less than equal to sum of the infinite series summation bn. This is what we proved. We also made some slight modification. The modification was, let us say there is an n, so that for every n greater than or equal to this, we are having the same thing. Then what do I know is, if summation bn, n is again greater than or equal to 1, is convergent, that would imply summation an is convergent. But this time I will not be able to compare the sum of the infinite series. That's it. Now there is a second version. It's essentially in some sense contrapositive in some sense. Suppose summation an with the same hypothesis. What is hypothesis? Remember, this is important hypothesis, an less than or equal to bn. So summation an is divergent. Do you remember what does it mean to say it's divergent? It's not convergent. Then summation bn is divergent. This is the second part, right? The proof is easy. Remember, let's look at summation bn. I want to know whether it's divergent, right? Now what do I know about bn? Bn's are non-negative. Therefore, if tn is the nth partial sum bk b1 to bn, then tn is an increasing sequence, right? Therefore summation bn, this converges if and only if tn's are bounded above. The sequence tn is bounded above, right? So we are assuming summation an is divergent. And I want to prove summation bn is divergent, right? So let Sn be the nth partial sum of this, Tn be the nth partial sum of this. Then by relation, what do we know? Sn equal to A1 plus up to An, that is less than or equal to B1 to Bn, that is less than or equal to Tn. Right? Okay. Is that clear? Therefore, for all n, I have Sn is less than or equal to Tn. All these things we have seen. Okay. Now suppose this is convergent. Okay. We will arrive at a contradiction. If this is convergent, that means there is this t, a real number, so that for all n, Tn is less than or equal to t. Right? That would imply, since Sn is less than or equal to Tn, that's less than or equal to t, this will imply the sequence Sn is an increasing sequence and bounded above. Why its Sn is increasing? Because Ans are non-negative. So that would mean summation An is convergent. This is a contradiction. Right? Okay. So pause, review, and proceed. Okay, let me quickly recall. So where you have a sequence that An is less than or equal to Bn for all n. Okay, they are all non-negative numbers. Right? Then I form the infinite series An and infinite series Bn. Then what is the first thing it says? If this is convergent, and if summation Bn equal to t, then summation An is convergent, and if S equal to summation An, then S is less than or equal to t. And the second version is, if summation An is not convergent, that is, it's same as saying divergent, then summation Bn is divergent. Okay, this is a comparison test. So, okay, so I'm going to tell you a trade secret. See, all of you in high school or in earlier courses, you must have learned about half a dozen to dozen types of tests for convergence of infinite series, right? And it's always a kind of a problem which test to use to check whether it's a given series is convergent or not. The important thing for any working analyst, the comparison test and the convergence of geometric series or otherwise, this is the most basic thing. I call them as mother of all tests. So let us give an application. So let 0 less than p less than 1. Let us look at the series 1 upon n to the power p where over n. Okay. Typically, for example, let us take p equal to half. Okay. So what is the relation between root n and n? Root n is less than or equal to n. If n equal to 1, it is equal to, otherwise it's strictly less than. Okay. This follows, remember, if 0 is less than a, okay, a and b are positive, then a is less than or equal to b, if only if a squared is less than or equal to b squared. If you have gone through my videos on real analysis, every time I had used this, so you would remember that. From that it follows root n is less than or equal to n, and hence 1 upon root n is greater than or equal to 1 upon n. Right? Okay. So what do I do? Call this as Bn, call this as An. Now what do I know about the series An? This is our harmonic series. Okay, this we know is divergent. Okay, therefore I have Bn is greater than or equal to An, and summation An is diverges. Okay, therefore by the comparison test it follows summation Bn, namely 1 by root n is divergent. Okay, that's an application. So this is application 1. Okay, pause, review, proceed. Okay, now again let us stick to less than 1. What is the meaning of n to the power p? This is exponential p log n. Let's assume n greater than equal to 1, greater than equal to 2. N equal to 1, its n power p will be 1 to the power p will be again 1, because it will be e power p log 1. Log 1 is 0, therefore it will be 1. Okay, right. Now okay, n is fixed. Okay, fix n, right? Therefore n to the power p is this, but this is greater than equal to, okay, remember log n is positive if n is greater than equal to 2. Oh, right? No, we want yeah, 2 less than e less than 3, therefore I need at least greater than, so let me say log 3. Okay, n is greater than equal to 3, log n will be positive. Okay, but doesn't matter. Remember, x going to e power x is an increasing function because the derivative of dash x is e power x, and that is positive, right? Therefore what do I know? Therefore fix n, again if you want, not necessarily greater than equal to 0, but anyway let's keep it. Therefore p going to n to the power p, which is e power p log n, is increasing. Is it okay? Therefore in particular, okay, n to the power p is 0 less than or equal to p less than 1 is e power p log n, that will be less than or equal to e power, when p equal to 1, log n, that is n. Are you following? Therefore 1 upon n to the power p will be less than or equal to 1 upon n. Sorry, 1 upon n to the power p is greater than or equal to 1 upon n. Right? In particular p equal to half. We already saw that. Yeah? So again by comparison test, so this is my bn, this is my an. I know summation an is divergent. Therefore summation bn, namely n 1 upon n to the power p is divergent for 0 less than p less than 1. In fact equal to 1 also. Up to that we know. Yeah? So pause, review, proceed. So in general the series of the form n to the power p, okay, where 0 less than p less than infinity, this is called harmonic P-series. So what you have shown is, okay, harmonic P-series is divergent, that is it does not converge if 0 less than p less than or equal to. That's all you have proved. Okay, this is what conclusion. So what happens when p is greater than 1? We have to look at it. We will do it. Okay, right. So should I do it now or a little later? Okay, let us do it later. Let's do it now. Okay, so let us look at, see, fix a p greater than 1 now. Okay, then let's look at the I'm going to group the terms now. 1 by p by 3 to the power p. How many terms are there? 2 terms are there. Each of the term is less than or equal to 1 by 2 to the power p. Right? This is less than or equal to 1 by 2 to the power p. This is also less than 1 by 2 to the power p. Is that okay? Right? Therefore this is less than or equal to 2 by 2 power p. Remember how I did with harmonics series, summation 1 upon n? The same kind of grouping I am going to do now. Okay, now let's look at next. So this is 2 terms. Now I will take 2 squared terms. 1 upon 4 to the power p by 1 upon 5 to the power p, 1 upon 6 to the power p plus 1 upon 7 to the power p. So each one of the term will be less than or equal to 1 upon 4 to the power p. How many terms are there? 4 terms are there. That is 2 squared by 2 squared to the power p. right? This is therefore it by 2 by 2 to the power p squared. Are you following? This is 2 to the power p. Yeah. Next, what is the, I take 2 to the power 3, that is 8 terms. That will start by whatever it is, it comes below 1 8 to the power p, and so on. It will go up to 1 15 to the power p. But each, how many terms are there? 8 terms. That is 2 to the power 3 equal to 8 terms are there. Okay, each one of them is less than or equal to 8 to the power p times 8. That is 2 cubed times 1 upon t cubed to the power p. Right? Therefore, these 8 terms less than or equal to 2 by 2 to the power p times power 3. This is 2 cubed. Are you following? Therefore, let's look at the nth case. So, nth case, where will it start? It will start from 1 by 2 to the power n power p. Right? 2 cubed power p. Earlier, 2 squared power p. P equal to 1, 2 power p. You understand the pattern? So, up to what it will go? It will go up to, where will it go? You go to 2 to the power n plus 1 and then minus 1. You see that? This is 2 power 3. Therefore, it will go up to 2 to the power 4. That is 16 minus 1. Therefore, 2 to the power n plus 1 minus 1 to the power p. This is just to kind of, okay, test your stamina. Okay, there is nothing more. Okay, you should not be flustered or confused with the notation. If the ideas are clear, you should have the confidence that you can write it. That's why I'm trying to explain in detail, right? So how many terms are there? There are in all 2 power n plus 1 terms. This starts with n and it goes to n plus 1, right? 2 power n plus 1 minus 2 power n terms. That is 2 power n into 2 power 2 minus 1. Therefore, there are 2 power n terms. Right? And each one of the term is less than or equal to 1 by 2 to the power n to the power p. And there are 2 power n terms. Therefore, these 2 power n terms are less than or equal to what? These are going to be less than or equal to 2 by 2 to the power p to the power n. Now see the pattern. Okay, that's most important. Now remember, this is, if I want to look at s 2 to the power n, what should I do? I should start from 1 and 1 by 2 to the power p and so on, 1 by 2 to the power n power p. You follow that? Yeah. So what I am doing, I am starting with 1 and then these 2 terms, then this will be 4 terms, this will be 2 power n minus 1 terms. Are you following? That's what I have been doing. Yeah, make sure that you understand. So each one of them is less than or equal to what? Let us call r equal to 2 by 2 to the power p. Therefore, this will be less than or equal to r. Next one will be less than or equal to r squared. Just go back. For 4, what did I get? 2 by 2 to the power p squared. That is r squared. And nth term, what did I get? R to the power n. But remember, I am stopping at 2 power n. Therefore, it will be r to the power n minus 1. Where r is this. Pause, review, proceed. Make sure you understand this. Right? Okay. Now let's go back. So I am looking at the series 1 upon n to the power p n, and I saw this particular partial series 2 to the power n is less than or equal to 1 plus r to the power n minus 1, where r is 2 by 2 power p. Okay, right. Now what do I want? When I want to show this is convergent, if I want to show this is convergent, I have to make sure, yes, remember these are all positive terms. Therefore, I have to show, I know this is increasing, therefore I have to show essence bounded above. Right? And remember, for each n is less than or equal to 2 to the power n, and hence Sn is less than or equal to s to 2 to the power n. Right? So enough to show s2 to the power n is bounded above, right? But what is s2 to the power n? It is 1 plus r to the power n minus 1, right? Now remember, this is okay. If 0 less than or less than 1, okay, we have seen the geometric series converges, and this is the nth partial sum or n minus 1th partial sum of the geometric series, and it's less than or equal to, okay, are you following? Okay, let Tn be the nth partial sum of the geometric series r to the power n starting from 0, right? And remember, when r is less than 1, this is convergent. And what is the t? T is the LUB of Tn. That we know is 1 by 1 minus r, right? Therefore, if r is less than 1, I know this is less than or equal to 1 minus r, right? Therefore, s to 2 power n is less than or equal to 1 by 1 minus r, where r is again 2 by 2 power p. I want this to be less than 1. Okay, so is r less than 1? Okay, that is clear because 2 is less than 2 to the power p, since p is greater than 1. Yeah. So what I have shown now, I have shown that s to the power 2n over p is increasing sequence and bounded above by 1 by 1 minus r, where r equal to 2 by 2 to the power p for p greater than 1, right? And sn's are less than or equal to s to 2 to the power n. Therefore, I know each sn is bounded by 1 by 1 minus r, where r equal to 2 by 2 to the power p, p is greater than 1. So what do you think I have proved? I have proved if p is greater than 1, the harmonic P-series summation 1 upon n to the power p, so this is over n, is convergent, right? So let us conclude. To conclusion, let 0 less than p less than infinity, and look at the harmonic P-series n to the power p. Okay, then 1, if 0 less than p less than or equal to 1, the harmonic P-series is divergent. And 2, if p is greater than 1, the harmonic P-series is convergent. Okay, go through the thing, pause, review, proceed. I just went through slowly because this kind of estimate, if you want to master analysis, this kind of easy estimate you should learn to work with. Okay, right. Okay. Now let us look at another thing. This is the so-called, do you remember, if I have a sequence an of real numbers, okay, then an is converges to a if and only if an is convergent. Let us say an is convergent if and only if the sequence an is Cauchy. Okay, this is a well-known result, right? So now I can ask whether this is called the Cauchy criterion. For convergence of a sequence. So now I can ask a question whether there is a Cauchy criterion for the convergence of a series. Yeah, it's still on. Okay, let us look at. So let see a sequence an is given. Let us look at the associated series, infinite series an. Okay, suppose this is convergent. Assume this is convergent. Okay, what does that mean? Remember, whenever I have infinite series, I look at convergence. What should I look for? I should look for the sequence of partial sum. Therefore, this is same as saying the sequence of partial sums is convergent. Right? Okay. Now since this is convergent, this is a sequence of real numbers. Again, its complex number is the same, but let me see. This is convergent if only if the sequence Sn is Cauchy. Right? So what does this mean? That means that is for any given epsilon positive, there exists a natural number n, so that for any m and n greater than or equal to n, modulus Sn minus Sm is less than epsilon. Right? Now let us assume n is greater than or equal to m, because n and m are integers. By law of trichotomy, either n equal to m or n is greater than m or n is less than m. With our loss of generality, we will assume n is greater than or equal to m. Therefore, what is Sn? That will be a1 plus am plus am plus 1 plus an minus a1 plus am. That is am plus 1 plus an. This should be less than epsilon. Do you follow that? Yeah. So therefore, this is, I have is infinite series, and it is convergent if only if the sequence of partial sums is convergent. But the sequence of partial sums Sn is convergent if only if the sequence Sn is Cauchy. Okay. That means the sequence of partial sums Sn is convergent if only for every epsilon positive there exists a natural number n, so that for all m and n greater than or equal to n, modulus Sn minus Sm is less than or equal to epsilon. But that is same as saying the sequence of partial sums Sn is convergent or it is Cauchy if and only if there for any given epsilon there exists a capital N, so that for all n and m greater than or equal to n, we have mod am plus 1 plus am plus 2 plus an is less than epsilon. This is called the Cauchy criterion. For the convergence of an infinite series. Okay. But in this form, it's very rarely used. But you can see almost all our textbooks, they keep on writing. Sometimes they even write something like this. Okay. There exists n, so that for all k greater than in n, something like that. an plus 1 plus an plus k or some such thing is less than epsilon, or all such things. You will see in old textbooks, they may even write such thing. But do not ever worry, this is very easy. What you should think of is, look at the partial sums Sn, that sequence is convergent if only it is Cauchy. And you know how to write down the Cauchy condition for a sequence of real numbers. You write it. And if you want, you know what is the definition of Sn and work out. Okay. So you should have confidence. So in fact, this formulation, okay, is very rarely used. But this is very important. This formulation is very important. Okay, pause, review, proceed. Right? Now, an immediate application is the following corollary. Right? So let an be a sequence in R. Okay? Let summation an be the associated infinite series right. Then if summation an is convergent, what does it mean? Okay, we know the sequence of partial sums is Cauchy, but let's look at something. Okay, I just want to see, I don't want to write it here, I'll come back. So suppose let epsilon be given. Okay, right, then I know there is a natural number n, right? Okay, then what happens? Let's look at. Okay, then what do I know is for all n greater than or equal to m greater than or equal to n, something happens. What happens? Modulus am plus 1 plus etc plus an is less than epsilon, right? You follow that? Right. Now let us look at, now my n equal, okay, m equal to n minus 1, that is, yeah, m equal to n minus 1. Therefore n will be greater than equal to m, and this is greater than equal to capital N. That is n minus 1 is greater than equal to n. You understand that? Therefore what, okay, then what will happen? I have only a m plus 1, that's it, which is already n. This is also equal to n. That should be less than epsilon. Okay, what does it mean? That means for every m greater than equal to n, mod am plus 1 is less than epsilon. Are you following? Yeah, right. See, for all n and m greater than equal to capital N, something happens. Okay, now I am choosing this to be n minus 1 itself, such that n minus 1 is greater than n. Right, then what happens? The mod an is less than epsilon. So for all n, if you want, is greater than equal to something. M itself is greater than equal to n, therefore in particular for n greater than equal to n, this is a true statement, mod n. So what does it say about the sequence? It says an converges to 0. Do you understand? Okay. Usually they will say nth term, okay, the teachers will write in textbook, they will say, okay, that is, if summation an is convergent, then the nth term goes to 0. This is what usually textbooks will say, and teachers will also write. But we are going to cast it in a modern way. Remember, when I want to talk about infinite series, I have to start with a sequence of numbers, right? Then I get the associated sequence of associated infinite series, right? So if this associated infinite series is convergent, then the original sequence an with which you started converges to 0. Please understand this. Okay, usually the textbook won't write it. They will only say this, or they sometimes write limit, which of course says this is 0. Okay, but the way I look at it different, slightly different. I am starting with the sequence an. I get the associated infinite series summation an. The associated infinite series is convergent. Then the given sequence an is converges to 0. So what does it mean? So you cannot if I start with an infinite sequence am which does not converge to 0, then the associated infinite series is not convergent. Do you follow that? Therefore, okay, convergence of an to 0 is a necessary condition for the convergence of the series. You understand? So in other words, if I start with a sequence am of real numbers which is not convergent to 0, it may be convergent also, okay, it may be also convergent, but if it does not converge to 0, then the associated infinite series cannot be convergent. Okay, try to think of it slightly different way. Okay, but this condition is not sufficient. This also we know. How do I know that? Because if I take an equal to 1 by n, then I know the sequence an goes to 0, but the associated infinite series, that's a harmonic series, is divergent. Therefore we know the condition is not sufficient. Is that all right? Okay. Now let's just quickly do things. Suppose I have two sequences, the associated infinite series, until assume they converge. Okay, the sum of infinite series a n is alpha and summation of infinite series is beta. Right? Right? You understand that? Okay. So the infinite series a n is convergent and its sum is alpha. Remember, when I say the sum is alpha, what should I think of? I should think of the sequence of partial sums Sn. Sn converges to alpha. And similarly, if I think of summation Bn, and when I say it is convergent, its sum is beta, what does it mean? Let Tn be the nth partial sum of the series summation Bn, then Tn is convergent and Tn converges to beta. Okay, that is the meaning of the sum. Always remember, okay, do not think of a finite sum and try to fiddle around as you do in algebra. Okay, now I have a new sequence an plus bn, right? Therefore I have an associated infinite series an plus bn. So what is the question I should ask now? The question I should ask is whether this is convergent. 2. If so, what is the sum? Right? That's very easy. So let us look at, okay, let me look at, I had used STUN, so let UN, okay, be the nth partial sum. Remember, whenever I want to look at convergence, what should I look at? I should look at only the nth partial sum, right? This is over n. Therefore, what is UN? UN will be A1 plus B1 plus AN plus BN, the first n terms. Now remember, it's a finite sum, therefore I can group terms together. Therefore I can write it as A1 plus AN plus B1 plus BN. Okay, I can use commutativity, associativity, etc., etc. I can do this. Therefore my UN is what? Nothing other than Sn plus Tn. Right? Now question is easy, right? Like you can answer, right? Does UN converge? Yes. Sn is a convergent sequence converging to S. Tn is a convergent sequence converging to T. Therefore, by algebra of convergent sequences, you know Sn plus Tn converges to S plus T. Therefore, I know UN converges to, right? Therefore, what is the thing? Therefore, the sum of the infinite series AN plus BN, this is nothing other than a limit of UN, that is S plus T, that is the sum of the infinite series AN plus summation BN. Notice that it's not algebra. You are not manipulating, right? The manipulation took place at a finite stage, at every finite stage UN. Okay? After that, analysis takes over. You have to think of convergence, algebra convergence sequences to arrive at it. Are you happy? Okay. So let me stop the lecture with the last one. Now suppose C is a constant and AN is a sequence, and these are associated infinite series. Let us assume it's convergent and this is equal to alpha. Then I have a new sequence C times AN. Okay, and whose nth term is C times AN. So what is that I would like to say? I have the associated infinite series CAN. The nth term is CAN, right? So is it convergent? If so, what is the sum? So again, what should I do? Let Sn be the partial sums of this. Let Tn be the partial sum. If you want nth partial sum of summation CAN n, right? But that is equal to CA1 plus CAN. Now remember, these are finite sums, therefore distributive law is allowed. Therefore this is nothing other than C times A1 plus AN. But this is C times Sn. You follow that? This is where the finite thing comes, the algebra comes, where commutativity, associativity, distributive law, everything I can do at that finite stage. Okay? Therefore my Tn is CSN, Now where does it converge? Again by algebra convergence sequences, this converges to C times S. Therefore Tn converges, it converges to Cs. Therefore what does it mean? This series CAN n, okay, converges, its sum is this is therefore C times summation AN. In some sense, notice that this equal to this shows a distributive law for infinite sum, but I want this infinite series, the sum should be, infinite series should be convergent. Are you following? Please pay attention. Okay, this is how you enjoy mathematics. Earlier I had, what was I had? I had CA1 plus CAN plus CAN, right? That is same as C times A1 plus A2 plus AN. This is the distributive law, finite distributive law. Here what I have? This looks like C times A1 plus A2 plus AN plus dot 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 equal to, it says CA1 plus CA2 dot 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 plus CAN plus dot 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 dot. So in some sense infinite distributive law holds. But is it always true? No. What is the condition I am imposing? The infinite series summation AN is convergent. So only for that case it is true, right? So now let us look at, okay, let V be the set of all sequences AN so that summation AN, the infinite series, is convergent. Are you following? Right? Of course it's all real if you want in OR. Okay, now this is non-empty because the constant sequence 0 is there, because the associated infinite series is this is 0, we know. Therefore the constant sequence 0 belong to V. Remember, V is not the set of infinite series, it is a set of infinite sequences with some condition. What is the condition? The associated infinite series must be convergent. Pay attention. If you are going to learn functional analysis in future, this is the subtlety you should understand. Okay, the set V is set of sequences only. You understand? Good. And when does the sequence AN belongs to, when does it belong to V? Then there is a condition. What is the condition? The associated infinite series summation AN must be convergent. Okay, so does the constant sequence belong to this? No, that we are already seen, because associated infinite series is not convergent. And let's look at this series 1 by n squared. This belongs to V, whereas 1 by n does not belong to V. Are you following all these things? Right. Now on this V I have an addition. If you have AN and BN, there are sequences which belong to this. I want to define a new sequence AN plus BN. This is a sequence. I want to know whether it will belong to V. Right? Remember, this is not convergent sequences. Right? What should I check? If this has to be in V, what should I check? I have to check the associated infinite series, whether this is convergent. Okay, this happens if only if this is convergent. But do I know that? That's what just now I proved. I know this is convergent, it converges to this number. Right? Therefore, on V I introduce an addition, and what did I do? V is close under this addition. You must have seen an example of vector space of sequences or even convergent sequences. But what I am doing, remember, if any sequence AN has to be in V, it is convergent. In fact, it converges to 0. You understand? Therefore, this is a subset of, V is a subset of the vector space of all sequences that converge to 0. You follow that? Next, let us see a thing. Then I define C times AN, this sequence. AN is in again V. This is a CAN. I want to know whether this belongs to V. When does this belong to V? Then I have to check whether this associated infinite series is convergent. Okay, this is not CAN, C times AN. Okay, whether this is convergent. But we know this is convergent, it converges to C times AN, right? Therefore, on B, I define addition and multiplication. Therefore, this becomes a, you have to check, this becomes a vector space overall. If you look at C0, the vector space of all sequences converging to 0, okay, this you must have seen, AN plus BN is AN plus BN, this also converges to 0, and C is any scalar, then C times AN is AN, this also converges to 0, you know that. Therefore, this is a vector space. So what I have shown is V is a vector subspace. I wanted to introduce C0. Okay, I wanted to introduce C0 because I wanted to say the elements of V are sequences, and the only condition they need a sequence belong to V if only if summation AN is convergent. The infinite series, associated infinite series, must be convergent. If it is convergent, we know a necessary condition is the sequence AN is converging to 0. Therefore, every element, every sequence AN in V actually belong to the vector space C0, and on which I already have vector space operations, namely vector addition and scalar multiplication. So what I have shown is V is actually a vector subspace of C0. I hope you enjoyed this lecture. Okay, we'll meet again.